Okay, so recap, connecting to today. Last time we started with matter, right? And that matter can be classified into a variety of things. We broke matter down all the way down to atoms. Atoms are the building blocks of matter. They make up everything else that has mass and space. If you break up an atom, it loses its identity, but it is made up of different pieces. Okay? We're going to kind of take a side step from the parts of an atom and just focus on an atom itself right now. Okay? With this idea of an atom, we want to be able to visualize what's happening at this molecular view, right? Once again, referencing our chemistry triangle, we want to be able to, what do we see and what do we can't see? Sometimes that picture of what we can't see is going to look like a kindergarten type picture, because we're just going to use colors and shapes to represent atoms. But it's a starting point to get us somewhere. So what we're going to do to start here is we are going to draw a picture of what this sentence is describing. Okay? So it tells us that we have nitrogen gas reacting with oxygen gas to form this thing known as dinitrogen trioxide. Okay, now my little key I'm going to use, and if you have different colors, you can use them as well. If you don't, I'll use different shapes, so that works too. So I'm going to use, so nitrogen symbol is N. I'm going to draw nitrogen as little circles. Okay, and oxygen I'll draw as little triangles. Okay, now as we are visualizing and drawing atoms and elements, there's something particular about 7 elements that we need to know, and I left the list up actually right there. There are 7 elements that are classified as diatomic. Make this list off to the side somewhere. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine are called diatomic elements. I'll give you a second to write those down. Does anyone know what the prefix di means? Yeah, I saw like your holding finger. So it means 2. So these 7 elements, excuse me, are unique in the sense that they do not exist in the world, in the universe, as ever a single atom. Okay, think of them as that friend who can't handle being alone. Right? They always have to have a buddy. So in nature, they come in 2s. So literally when you breathe in oxygen, you're not breathing in a single O at a time. You're breathing in O2 molecules because it's always bonded. Okay, so this is how oxygen always exists. Same thing with all of them. Okay? Now there's 2 ways that can kind of help you remember the diatomics. One way is if you say this as a word, it says Hofbrinkel. So if you just remember Hofbrinkel, that tells you all 7. I didn't make that up. Someone taught it to me. Or, where's my stick? See a stick somewhere? Oh. Brinkelhoff? Sure. Here's my way I like to remember them. Okay, so how many are there? 7. So go to number 7, okay? And then draw, watch my stick, draw a 7.
Because you always have a periodic table with you?
Yes, you'll always have a periodic table.
That is only 6, wait, what?
No. 1, 2, 3. Oh, and hydrogen. That's the one thing it doesn't have. Yes. So it gets most of them, except you gotta remember hydrogen. So.
Wait, you stack periodic tables?
Oh, yes, yes, yes. Yes, yes, yes.
That's why that's always up there.
Yeah, so it's not about like we memorize the symbols for efficiency, but besides that, it's never about memorizing the periodic table, it's just learning all the tricks of it. So, okay, so that means when we draw, so we have nitrogen floating around, we need to draw as this, because it comes in 2s. If it wasn't diatomic, then it could exist as a single thing. Okay? All right, it says nitrogen gas reacts with oxygen. So we have two, because oxygen's also diatomic, floating around in there as well. Now, would this together be classified as a pure substance or a mixture? Very good, a mixture, right? Because they're not linked. This by itself is pure. This by itself is pure, but when they're together, that's just a mixture. Okay? It's turning into this thing known as dinitrogen trioxide. Now, I will teach you how to do naming and formula just as we go. But we'll kind of learn some things, little pieces along the way. So what did we say di means? Two. So that means I have two nitrogens again. What do you think tri means?
Three. But then, friend. Can they be just friends with each other?
Yes. So by the whole thing, it can't exist by itself. It doesn't have to be a two. It just can't be, in this case, it has lots of friends, so it's good.
So what did the third oxygen come from? It was always there. But we couldn't open it.
No, great observation. There's something wrong here from that side to this side. What happened?
An oxygen appeared.
Yeah. We had only two triangles on this side, and now we have three triangles on that side?
And spontaneously came into existence.
Just a triangle fell from the sky. Yeah, Evan.
Would we need to do more nitrogens and oxygens on the other side?
Very good. So yeah, as written, as we've drawn it, if I only had one of these and one of these, this reaction would not happen. Because things cannot be created from nothing. Okay, one of the most foundational laws in science, it's the first law of thermodynamics, it says that matter cannot be created or destroyed. It can move, it can rearrange, but it can't pop up and it can't go away. So if I only had one of each of these, nothing would happen. So let's throw another oxygen in the mix. But do they come as just a single one?
No.
Nope, it comes as a pair.
No, but then it'll be alone on that.
So now we have that.
Are we adding fractions?
Okay, I see some ice. Do we kind of see where we're going here? So now we have the problem of, okay, this can't be alone. Right? So what should I add more of?
Another green and a red. Wait. Or a green and a blue.
So if I add another set of these and another set of this,
Then it'll be okay.
how you connect your circles and triangles, by the way, does not matter right now. Right? As long as they're connected, that's really what we're going for. Okay. This is now what we would call a completely balanced reaction. Yeah?
Could we have just added another triangle into a line of two triangles over there and just made it two circles and three triangles?
Ooh, great question. No. Because how they exist is how it has to come. And nitrogen doesn't ever exist in threes. It exists as twos.
Does it exist as fours and sixes or just twos?
Just twos. You can have lots of twos, but just twos.
So how did they split up?
So in the reaction, because they made this new thing, then they can
So
split.
it doesn't have any rules at least.
Very good. Yep, because it's created something new. So this arrow is very significant in the fact of things are changing, things are moving and rearranging in the process. Great question. Okay, we're going to translate this picture now into, so this right here is like the molecular side. We're going to change it into the symbolic form of a chemical equation, so how we would write it. Okay, so I have two N2 molecules. Now these numbers are very important in what they represent. The big number in front is known as a coefficient. This tells you you have two separate things. The little number is indicating that it comes in twos. This right here is known as the subscript. And it indicates the bonds. Okay? Now we have two N2s. A plus sign is showing, hey, they're coming together, but they're not together yet. 3 O2s. Just to reemphasize here, 3 O2s is not the same as 2 O3s. Yes, because this would mean you have 3 oxygens bonded together. These one are only comes in 2s. This is actually ozone is O3, which is not the same as pure oxygen. Okay? Okay, for a smiley face with your table buddy, fill in that blank. What would I write after the arrow to represent this? Ready, go. Write it on your paper. So are you saying there's 2 in front because you have 2 nitrogen?
No, yeah.
So the one in front should indicate how many of the sets you have. The small one is telling you what's going to be right. 1, 10,
Okay, that's what I was asking. I didn't know.
that's what you're asking. Okay. If you have 2N2O3, you can have a smiley face. Now, technically, you also could have said, in our case, if you did that, that's technically right too, in our understanding for now. So, yeah, Taylor. Not today. But I should have them next time. I finally figured out I was sending my email requests to the wrong person for copies. So that's why my copies weren't getting made. So, yeah.
Is the order of the elements? Is that how you order them?
Kinda. There is, when we start learning how to name and formulas, there is definitely a trend of their positioning for sure. So,
A trend.
yeah. Okay, questions on that? Now, next thing we need to understand here, so this right here is called a balanced chemical equation. A balanced chemical equation shows that it's following the law of conservation of mass, meaning nothing got created, nothing got destroyed, everything that was here, the Lego pieces on this side, are still here on this side, they've just been restacked, right? A balanced equation is just the recipe though. It doesn't exactly mean that's what you have in your experiment, okay? Because in your experiment, you could use whatever you want of amounts. Let's say in this case, you don't have to draw this, but just to have a visual, I could do this reaction and it would still work, even if I had these in there as well. This would still turn into that. The difference would be I'd have leftovers, right? In chemistry, we call them excess. And that's fine. It's still balanced. So be aware that the numbers up here don't tell you that you have to have 2 and 3. That's the perfect ratio, but you can always have more and you'll just end up with leftovers. But it is critical if you don't have enough of the ratio, then it won't happen. Right? If you don't get enough of it, then it will stop. Okay? Now, we draw it this way, but when it comes to going into the lab and seeing it, it is impossible and not logical to actually measure out 2 atoms or 2 molecules of nitrogen and just 3 molecules of oxygen. Like, atoms and molecules are too small for us to actually measure out individually. So scientists, well, one particular scientist came up with a way to group them together so we can work with them on our level, right? Because our level down to the atom level is so different, we kind of need a bridge a little bit. So we're going to watch this video, and then we'll talk more about it.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particle. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay. Let's talk about this mole. Okay? So, I don't know why they named it the mole, by the way. Mole is just the word they chose, right? All units just have a name for whatever reason. But a mole is just another unit. It's primarily used in chemistry, which is why maybe you haven't heard it before. If you have, it was in a science class. Okay? But the best way to relate a mole is think of it like a dozen. Okay? If I have a dozen markers, how many markers do I have? Why?
Because that's what it does.
That's what it is, right? If I have a mole of markers, how many markers do I have?
2 times 10 to the 23rd markers.
Good. So 1 mole of anything is 6.02 times 10 to the 23rd. Now, it is such a big number. Why? Why do we need such a big number?
Because atoms are super small.
Atoms are so small, right? So to give you some more visuals here, this right here is a mole of salt. How many atoms are in this? 6.02 times 10 to the 23rd, right? That's how many atoms are in this little container, right? Insane. Atoms are so small that we needed a really big number to group them together.
Atoms or
Molecules would have been the correct word there.
Okay,
There you
that's
go.
what I
Thank
was
you.
gonna ask.
Okay, now, Aaron, will you be a human scale for us? So put your arms out like this. I'm gonna put these in your hand and just show them like the difference. And then pass them around. Okay, so 2 things right here. First off, so this is a mole of one thing. This is a mole of another thing. First off, are they the same size? No. They're not the same weight either. I'll pass them around, but like this one's a lot heavier than this one. So how's that possible? How can this be a mole and this be a mole, but they not be the same size or the same weight?
Well, if you have like a dozen chickens and a dozen donuts, they're not gonna weigh the same. It's just like the same as a dozen.
So what's the same about them? Matt?
They both have the exact same amount of molecules in them.
Yeah.
Because like maybe the molecules in one are like much heavier than the molecules in another.
Very good. It's just a counting unit, right? It's just like a dozen. It just counts things. And so yes, when you're just counting things, their masses aren't going to be the same, their volumes aren't going to be the same. They could be, but most likely it won't. Okay, so I'll pass these around. I guess I'll pass around. Is anyone nervous about passing these around and touching them? It's like, yeah, it's pretty fine. So there's actually 4 different samples here. They're all 1 mole of that thing. So, okay. We established this is a counting number, right? Unlike a dozen, though, we have a dilemma. I can count out a dozen of something. I can't count out a mole of something. Even if we could see atoms, you would die before you could count this high. There's not enough seconds in your life to count to a mole. So the next connection is scientists found that 1 mole of something, okay, is equal to the mass in grams. To give you a concrete example, let's pick lithium. So if I have 1 mole of lithium, it would weigh 6.941 grams. So if I told you, hey, will you go into the lab and get me a mole of silver? How would you get that? Or what would you do? Once you find silver,
Oh, I would guess 100.
you would go and weigh out 107.868 grams of it. Okay? All right, smiley face question. Don't say it out loud. Just find it on your paper. If I wanted you to find, I had this last year, but it evaporated over the summer. I want to put 1 mole of water in this container. How much water am I going to put in here? Talk with your table buddy. Find me an answer.
So, yeah, 200.
Yeah, you have. You don't, I mean, you don't have to talk. Or out loud.
Yeah. So now,
Carly, you can join us.
it's 17.9.
Yeah.
Wait, yeah, there's 2.
The sign in this class to show me that you're done when I like give you a problem to do is to drop your pencil on your paper. Give me a pencil drop. Then I know you're ready. If you're not ready, keep holding your pencil. By the way, if you have a calculator, I would pull it out right now because we're going to be doing lots of calculations. If you don't have a calculator and would like to borrow a calculator, you can raise your hand. I would try to get in the habit of having a calculator for this class all the time. It's better to use the one you're familiar with. Okay, everyone have an answer? Okay, on the count of 3, shout your answer out. Ready? 1, 2, 3.
18.
Good. It's about, depending on your rounding, 18.02 grams. Okay? I think as I walked around, we're on the right track, but just make sure, since water is H2O, you have to add up 2 hydrogens and 1 oxygen to get the entire mass of it. This number right here is known as the molar mass. The molar mass is the mass in grams of 1 mole of something. Okay? Now, what's cool is the molar mass is proportionate to a single molecule's mass in a different unit. So a single molecule of water has a mass of 18.02 as well. The unit just changes to an AMU, which is atomic mass unit. It's the unit we use for atoms because they're so small. But we can't work on this scale, so we work on the scale of grams. But it is proportionate. They're the same. Okay, any questions so far? Okay, so now what we're going to learn is how to connect these different units together through a series of what is known as conversions. Converting is something that you might be familiar with from other classes. I'm going to teach you a very particular way I want you to set up conversions in this class. After you prove to me that you understand and are good, if you don't want to use this method anymore, you don't have to. But I trust in it so much that I need you to do it in the beginning until I know that you are capable of not showing me as much work possibly. Does that make sense? Also, showing your work on the AP test for the non-multiple choice section can actually be very valuable in maximizing your points. So it's a good habit we want to keep up, okay? All right, let me erase this. Okay, so our problem here says, calculate the number of atoms in 3.40 moles of C6H12O6. Now, something you're going to hear me say all year long, because we're solving problems all year long, is the first thing you should do when you read any question in this class is circle what is it you are trying to find. Because AP questions are going to get very long and very wordy. And so we need to be very good at making sure we know where we're headed, because that sometimes is the hardest part. It's like, what am I even trying to find? So in this question, what is it wanting me to find? Atoms of what?
Hydrogen.
Okay, so I would circle that. Circle atoms of hydrogen. Have a goal of, okay, this is where I'm headed. Okay? Next step in problem solving is then to underline anything that is given to you in the problem that's going to help you get there. So what information is given? Good, so underline this. 3.50 moles. Next step, I'm going to take what's given and I'm going to put that on my paper first. Now in chemistry, numbers always need labels because they have meaning, and they always have two labels. They have the measurement label and the, what would you call this? What it is label, right? So we're measuring in moles and it's moles of this. By the way, you can abbreviate the word mole by dropping the E. I don't know why I do it all the time because they say it's okay. Don't know why they abbreviated a 4-letter word. But just so you know, I typically won't write it. So, okay, now the way to do conversions, and this is outside of AP chemistry. This is just the way conversions work, okay? If I have, let's say I measured something at my house, and I measured it to be 36 inches, but I need to know how long that is in feet, how would I relate those two? Yeah.
You could divide it by 12 inches.
Good, so I think we all understand if I divide this by 12, it would convert it into feet, right? Why does that work? Good, there's 12 inches in a foot, right? The way conversions work mathematically is that the thing you are relating is equivalent. Literally, mathematically, we are timesing by 1. Because if this equals this in math, it equals 1. And if you times by 1, you're not actually changing the value. You're just changing how it looks. So one of the biggest things is when you set up your conversions in this class, they have to equal one another if you're going to put them on top. If they don't equal each other, you can't relate it through at least a single step, because it wouldn't be true anymore. Okay? So that was just kind of a side note. So I'm going to set up my first fraction here. The way I think about conversions is by tracking the units. I create it like a pathway. Okay? I'm in the unit of mole, and I don't want to be in the unit of mole anymore. So I'm going to put mole on the bottom. I'm going to be very strategic here with how I use my different colors, by the way. Okay? So notice that mole is here, and mole is there. Notice also, I don't have a number yet. I let the units guide my process, and then I go back and worry about the numbers. Okay, what am I trying to convert moles into? Atoms, right? Okay, now terminology here is going to be a little off, but just stay with me. Okay, so I'm just going to say atoms of C6H12O6. connection between the mole of something and atoms of something?
6.2.
That number.
02 much.
Good. So 1 mole of anything equals 6.02 times 10 to the 23rd atoms, or anything technically. So I'm going to put, let's use screen. To 1. Because there are that many atoms in 1 mole of something. Now, going back to my question, what am I trying to find? Just H. So we've gotten it down to atoms of this, but we now have to take it a step further, so add a second conversion. I don't want this anymore, so that's the unit that goes on the bottom. What I do want is just, whoa. Atoms of H. And atoms of one thing are related to atoms of another through what relationship? Or what numbers would I plug in there? Good. Because there's 12 H atoms in one of those. Now that's where I say the terminology is a little weird. Technically this isn't an atom, right? But, yeah.
Wait, if you were finding like all atoms, would you have to do like 16 times 6?
No. But great question. What is that 16? What unit does that refer to? Grams and mass. So we will start bringing that up, but when it deals with grams.
Okay, so the atoms is
Just how many you have. Yep.
oh, okay.
Yep. So if it was oxygen, the difference would be you'd have 6 atoms to 1. Does that make sense?
Yes.
Good question. Okay, then once this right here matches what you have circled, you know you're done. So we can then plug it into our calculator and get the answer.
But just the numbers.
Okay, so here are your options for plugging it in. You can plug them in as actual fractions. To me, that's the longest way to do it, and we're all about time, so I don't plug it in that way. The way I type in conversion things is I type the first number, so this is what's in my calculator. Okay, so I would type 0.35. This is on top of the fraction, which means it's multiplying by it. So then I would hit times. How many of you know the shortcut on your calculator to type this? None of you? It's the coolest shortcut ever. Okay, on your calculator, now it depends on your type, but if you have a graphing calculator, you want to look for, it's normally above the comma. It's a capital EE. If you don't have that on it, the other button is, you want to look for EXP. This one's just right there. What that does is when you hit that button, so hit second comma, it should, on most calculators, it's going to look like this. And bring up a little E. Did that work for everybody?
Wait.
So type 6.02. And then hit second comma.
But why?
And then you only have to type 23. So this takes care of the times 10 to the power. So rather than having to type times 10 power of 23, you just do number E23. Does everyone understand that shortcut?
So, but if I were to write times 12 immediately after that, would I need to put parentheses, or would it include?
No, that's the other cool thing, is the E, in a sense, already puts this in parentheses for you.
Okay, that's why, because I was like, otherwise, it's not that helpful, but if it puts it in parentheses for you, then.
Yeah, it puts it in parentheses, and it's I know it's not much, but it is a little faster than having to type times 10 to the whatever. Yeah, Isaac.
Do you need to put the 6.02 before you type E or no?
Yes. Yeah, so type 6.02 and then hit the E and then the 23. If you need help with your specific calculator, because sometimes it is different, let me know. But that's how I would type it. Now, anything that's a 1, don't do, because if you divide by 1, you times by 1, it does nothing. So I did this times this. I'm coming to the next fraction. I'm going to times it by 12, because the 12 is on the top, and that will be your answer. If it was on the bottom, hypothetically, you would hit then divide by 12. I know they're simple things, but in this class we want to be all about speed and efficiency. So I don't even remember what our answer is. Where's my paper? If you plug that in right, you should have gotten 2.53 times 10 to the 24.
Can we write the E instead of times 10?
Yes, yeah, you totally can. Yep, you can use the E in your answer as well. Now, all answers need 2 units as well. So what is this number? Good, so atoms of hydrogen. Don't leave numbers alone. They need a label. Okay, questions on setup or anything so far? Okay, I'm pushing you into the swimming pool to swim. Try the next problem with your table buddy. Ready, set, go. Yeah.
When you go 12 over 1, how can you get like
So each fraction by itself.
it's just equaling 1?
Yes. So, well, and it's the thing that really each fraction is pretty independent of the one before, right?
Yeah.
So if you just look at this by itself, in one atom of this, there are 12 atoms of each.
Okay.
Does that make sense?
Yeah.
So you should always be able to translate a fraction into an equal sentence.
Because it's the same.
Like, that's
What is,
It all depends on what you're looking for. In this case, they were looking for atoms.
yeah, like how the atoms are all
It said how three were So what you did is not wrong. Try the next problem and then give me a pencil drop when you're done.
So, does that do
but like, where do we do it?
yeah, basically.
Is it 5? But it might be.
What it's saying is that there's 2 of this per molecule, so 2 of those which should be of 6.
Yeah. Yeah, like they're saying it's probably 6 times from the same. There's 2 of the N of 3s. So I guess N of 3s is just common pairs.
Alright, I'm gonna put it in the board. Which exhibit is it?
Okay, looks like we're almost there. I see some good answers. Okay. All right, if you got an answer about 9.0 something times 10 to the 23rd, you are correct and can have a smiley face for that. It's 9.03 times 10 to the 23rd about. Okay, any questions? Yeah, Carly. Not the last one, but more to come. Okay, any questions before we learn one more step to this?
Can you show us the equation for that one?
Oh yeah, the setup, for sure. Is this the right question? Yes. Okay, so I'm starting in moles. Okay, and I'm trying to get to atoms of oxygen. So first step is I'm going to go from moles of the whole thing and convert it down into, where did I put my other markers? Anyone see them? I was walking around with them maybe.
What are you looking for?
My markers.
Oh, I think they fell on the floor.
No? Ah! Bizarre.
Oh, they're right there.
Right here. That peripherals mess me up, right, with this math. Okay, so then I'm going to change that into atoms of the whole thing. And then you can go from atoms of the whole thing into just atoms of oxygen. I forgot to change my color, but it should be a different color. Okay, once again, notice the pattern, follow the pattern, but also understand how it works. Conversions are so logical if you don't just try to memorize this, then this, then this. Okay? I'm going from moles into atoms, and then I'm going from atoms of the whole into atoms individually. The things on top of each other have to be connected. So the thing that connects atoms and moles is always Avogadro's number. That's 6.02 times 10 to the 23rd. Okay? Now, a common question people will ask is they would say, well, how do I know that this goes on the top of the fraction, or does it ever go on the bottom of the fraction? Because it could go on the bottom at times. Isaac?
Would you put it on the bottom if you're changing atoms to moles?
Very good. Have a smile for that. It's all about the units. Okay? If I put it on the bottom right now, I would be saying that there are 6.02 times 10 to the 23rd moles in one atom. Doesn't make sense. That would be like saying that there's 12 feet in 1 inch. Okay? Make a sentence out of what you wrote, and it should make sense. Okay? Now, in this case, in one atom of the whole thing, there are 6 atoms of oxygen. Now, it looks like as I walked around, I didn't explain this, but most of you figured it out, which was what I was hoping for. In parentheses in chemistry, in terms of finding totals, it's just like in math. Just distribute. Right? So there's 6 oxygens, 2 nitrogens, but how many calciums? Just 1. That's why it's not inside the parentheses. So, yeah.
So I know that each fraction it equals 1 to like the whole, but like 6 oxygen atoms doesn't equal 1 of like the whole thing. Like, cause I feel like the 6 oxygen atoms is like a piece of the whole.
So what we're saying is that in the whole thing, in one of the substance, there are 6 oxygen atoms, right?
Yeah.
And so then when you times it through, it narrows it down to a single, how many oxygen atoms you have total.
Okay, that makes sense.
Does that make sense?
Yeah.
Okay. Any other questions? Kai, did that answer your question? Okay, This right here is your homework packet for Unit 1. Open it up to the very first page, which is labeled 1.1A for me really quick. There's never enough time in the day for AE.